So we're going to look at what's called direct variation. So when we're looking at linear relations, the way the values vary or change is what we're talking about here. So direct variation means that the y, or dependent variable, is equal to the x, or independent variable, multiplied by a constant number. So whatever, to find the y value, you just take the x value and multiply it by something. So here's the general formula, y equals mx. I believe the textbook uses kx, but most of your math teachers at the school will use mx as your rate of change. So this is that constant number, the m, that happens to be your rate of change. So the m value is your rate of change. So your dependent variable, your independent variable, and your rate of change that we use. Any graph using this formula, any direct variation, has to be a linear graph that passes through the origin, point 0, 0. Thus, it touches or intercepts the y-axis at the vertical axis at 0. So it's going to touch at this point here. Okay, it has to touch at 0. Okay, it has to touch at 0. This is called the y-intercept, or also the initial value. So the point that it touches the y-axis is often called the y-intercept or initial value. Initial value tends more when we have just a left-facing graph like this. The intercept more when we have the crossed graph like this. So that's our direct variation again. Y equals mx. Going to cross linear graph crossing through 0. So you'll have graphs looking like this, be it increasing, be it decreasing. So to do some example work with that, here's a problem we can work through. Gas costs $2 per gallon. Create a table of values for the price of gas up to 4 gallons and graph the table. So 0 gallons, 1 gallon, 2 gallons, 3 gallons, and 4 gallons would be the number of gallons we're buying here, 0 to 4. So if we buy no gas, 0 gallons, it's going to cost us $0. If we buy 1 gallon, it's going to cost us $2 because it's $2 per gallon. 2 gallons, so that 1 more gallon means it cost us $2 more bucks. 3 gallons, $2 more dollars. Boom. Need to actually add $2, don't I? $4, $6, 4 gallons is going to cost us $8. So there's our table of values, and now we want to graph that on the table here. So I'm going to use a blue pen here just to make it stand out. So 0, 0 is my first point. 1 and 2, 2 and 4, 3 and 6, and 4 and 8. So here's my points. Now, before I had a graph and mentioned that in a previous lesson that I didn't connect the points with the toppings on a pizza because it didn't make sense to have the 0.5 of a topping or 0.3 of a topping. But when we're buying gas, you can buy portions of a gallon. And if you ever watch the gas at the pumps tick up, you see that you have the fractional portions of gas. So in this case, it does make sense to connect the dots. And I think I'm going to put my ruler this way. So I'm going to connect the dots. So there's a line. So there's the graph with the full line there. Now, we want to draw a rate triangle on the graph. So when we do our rate triangles, when we're finding our rate of change, we can pick any pair of points on the graph. Picking points, we do not want to pick a point like this. Some people go, okay, well, that's on the graph. But if you pick this point right here, what number is that at? You can approximately say, oh, well, it's about 1.25, but are you sure it's 1.25? Or maybe it's 1.3. You can't really tell. So what you want to do when you're picking points on the graph is pick them where they intersect the grid lines. So on my graph here, they're in red, my grid lines, the ones that came pre-established on the graph. Pick points where the line crosses those grid lines. So here I know it crosses a grid line. I'm going to pick that point. And I could pick any point along here. I could pick this one, this one, this one. I'm going to pick this one here. So these are the 2 points I'm going to use for my right triangle. And so for my right triangle, I'm going to draw. It doesn't matter if you draw it above or below. As long as your right triangle makes a right angle, should be a right angle triangle. Okay? And then we'll count our rise and run. So our right triangle, it's increasing from 2 to 6. So that is an increase of 4. And then my run here, so rise 4, run is from 1 to 3, a rise of 2. So I went 2, 4, 1, 2. And pay attention to the scale. Notice my scale goes up by 1s on the bottom here, but goes up by 2 on the sides. So you need to pay attention to your scale because they can change depending on your graph. So there's my right triangle. So the question, part C says, what is the initial value? Well, the initial value is where the graph crosses the y-axis here. So that initial value is 0. The y value is 0. What is the rate of change? Well, the rate of change should be the rise over the run. So rise over run equals 4 over 2, which equals 2. So our rate of change in this case is 2, or $2 per gallon as a unit rate. We want to write an equation for this relation. So remember, we have that y equals mx as our general formula. This is the value we need to change, the m. The m is the rate of change. So y equals 2x would be our formula. We just pop in whatever the rate of change is. What is the cost of 12.6 gallons of gas? Well, can't figure it out from our table because we only go up to 5 on the table, but we got a formula. So we can use that formula. Y equals 2 times 12.6. The gas is the x-axis, along the x-axis, so that's why I filled it in for the x value. So we replaced x with that. This will tell us our cost. Our cost equals 2 times 12.6, which is going to give us 25.2. So the cost is $25.20 because it is a dollar value. Now, sometimes we don't need to do a nice perfect graph with a table of values and everything. So in that case, and my camera seems to keep tipping on me. I'm going to try to tighten that up here. Hopefully that's a little better. A card drive. So in this case of sketching, yeah, we don't need to make a full table and a fully plotted graph. We just need to make a sketch with some of the key, putting down the key values. This works well with linear relations. So we got a car driving an average speed of 60 kilometers an hour. Comparing the distance and time, would this be direct variation? Well, if the car is driving at a speed of 60 kilometers an hour, so that's a rate, that's going to be our rate of change. At 0 hours, how far would the car have traveled? 0. So because that would be the initial value. It would start at 0 kilometers. So the initial value is 0. And if the speed is staying that constant 60 that we're using as our average expectation, then yes, this would be a direct variation. The initial value is 0, and the rate of change is constant. So yes, it is, and there's a description of why. And that's sometimes good to do. It doesn't explicitly ask us anything more than yes or no, but we put down a description so that we can show our understanding. So now we want to write a relationship, an equation relating the distance to time, so we want to make that relationship. So the distance would depend on how long we traveled, so that's going to be our x value, and that'll be the y value. So you got y equals mx as our direct variation formula. We could change the y to distance. The distance equals the rate of change, 60, times the time, and we can use t as our x value. So we can use y or x, but in this case it makes sense to switch y and x to d and t for distance and time. And if we want to sketch a graph of that, so we don't want to make a big table here or anything in this case. These are going to be my distances. These are going to be my times. So it's going to be starting at 0. We've already established. And then we just look at that formula. It's going to go every one we go over. So the rate of change is the rise over the run, correct? And so it's 60. And we said before, we can change any number into a fraction by putting it over 1. So every time we go over 1, we want to go up 60. So 1 and 60 would be about right here. 2 and about 120, up another 60. 3 times 60 is going to be about 180. So about 50, 75, probably about right here. 4 and so we end up making a full table, but if we take a look, 5 times 60, we'll just do 2 points here, and it's good to do 2 points that are spread apart, so I'm going to skip 4, go right to 5. 5 times 60 is going to give us 300. So we know it's direct variation. We got 2 key points on there, and we can use that to draw a line. And my estimated points were pretty good. These two were actually really good. This one I was a little bit off. But the 5 was nice because it fit right on the grid line. So that's a quick sketch of the graph. It doesn't have to be perfect per se and wouldn't be expected to be the same as if you plotted a whole series of points. But it's a quick way to sketch the graph. We just find that a couple values. So recognizing 60 times 5 is going to give us a nice even 300. That worked well. But we could have stuck with even this and got a fairly accurate graph if we just use these 2 points right here. So again, direct variation, y equals mx is our general formula, dependent and the independent variable, and then m is our rate of change. We can use that to create a table and we can get that from a table and a graph and create that formula, or we can use the information we're given if we're given the rate of change and the knowledge that is direct variation to create a formula as well.